Okay, the clock is 10 a.m. here in Germany, and it's time to start our webinar. I hope everyone hears me well. So good morning, good afternoon, depending where you are. So this is the second webinar of our series. The title is today, Factors Influencing Accuracy of Mobile Mapping Data and Best Practices. My name is Joni Salo. I'm a support and training engineer here in Trimble. I'm located in Biberach, south of Germany, with the other support team members in our mobile mapping office. I hope everyone hears me well. If you don't hear me or there's any problems, let me know. So to start with the introduction for this webinar, we are having actually set of two interrelated webinars. So the session one is today. So this one we're having now, and we actually have a second session which is related to this one, and it's called Point Cloud Registration TBC. And the idea here is that to get full understanding of this whole setup of mobile mapping positioning. Sorry, can you see my screen? Oh, okay, let's start again.
Yeah.
All right. So this is the first slide I wanted to show you. So let's start again. This will be a set of two interrelated webinars. The first one today, and second session related to this one on 2 weeks actually about the point cloud registration in TBC. So today we're gonna talk about the field operations with the mobile mapping system, stuff like GNSS quality, IMU, DMI, base stations, planning of your mission, driving how you drive the mission, so on. We're gonna also talk a little bit about PostBack, which is the software to process the trajectory of the mobile mapping system. And then the second session will talk more about adjusting the data to known points, so ground control points. This is called registration done in TBC. So I strongly advise all of you to attend to both webinars if it's possible, so you will get the whole picture of the process here, let's say it that way. But for today, the goal is to understand different phenomena affecting accuracy of mobile mapping and to learn best practices to get the best out of your system. So for those who already have a system, I hope you will learn some new tips or tricks to get even better data. So I would say if you have a basic knowledge of mobile mapping, kinematic mapping, or surveying GNSS, you will get most out of this webinar. But also, if you're a beginner, you will hopefully get something out. Also, if you're an advanced mobile mapping user, I'm sure there's something you will learn today. I'm not going to go into very basics here because we only have 1 hour, so I'm not gonna start from the scratch with mobile mapping stuff and GNSS and stuff like this. But I'm gonna expect that the listeners have some kind of idea of these things. So today we go through these topics. So I'll start with explaining how accuracy is defined, what we think accuracy is. Then we're going to move to natural sources of error in positioning system, GNSS, IMU, DMI, and we're going to give you some best practices how to deal with these error sources on the field in the post-processing. Then I will shortly also talk about the error sources in measurements, so actually the laser scanners, in the imagery, the photogrammetry, and so on. Then in the end, I will also talk about calibration. This is something which, of course, affects the accuracy as well. And in the end, there's also something called error propagation model, which I'm gonna give you a couple examples on how we can kind of add everything from this webinar together to get a whole picture of the accuracy. So accuracy is a tough topic many times. What we use in the data sheets, if you look at the data sheet of Trimble mobile mapping systems, there's accuracy values. So these are called 1 sigma values. So this means that one sigma means that 68% of the measurements are within this value. So in the right, you can see this standard deviation figure. So 68% of the measurement should be within this value. 2 sigma would be 95%, and 3 sigma would be close to 100% of the measurements. Actually, this is what most surveying equipment manufacturers use. So the data sheets are usually, you can compare these. They should be the same values. Then another thing which is for surveyors, I think you should be very familiar, but we have something called accuracy and we have something called precision. Accuracy could be, you could say it's a description of systematic errors. So it's a difference between a result you get to the true value, what it should be. And then precision is more of a description of random errors in the measurement. So the deviation, if you do the same measurement over and over again, how much the deviation between these measurements are. So if you look at I have this kind of figure in the bottom. It should be like a target. So we are trying to hit the middle of this cross. So let's start from the left. If we have low accuracy and low precision, you can see we are hitting not the middle of the target, and we are also getting quite sparse measurement deviation. Then if we have high accuracy but low precision, we are hitting somewhere in the middle in where we want to, but still the measurements deviate from each other quite a lot. But if we have low accuracy but high precision, we are not hitting the middle, but the measurements are still quite close together. And then in the end, of course, the scenario, what we are looking for is the high accuracy, high precision. So we are hitting the middle of the target we want, and the measurements don't deviate from each other too much. You could also talk about absolute accuracy and relative accuracy. I would say absolute accuracy is how well your data fits into your reference data, which you know is well positioned. And relative accuracy could be something, maybe you measure a height of a pole in the data and how accurate this is. So this might be accurate, relatively accurate, but could still be off in the location. So this is the world of accuracy we talk about. And maybe I didn't mention in the start, you're able to ask questions through this GoToWebinar app. So please do. I will not look at the questions during this webinar, but we are going to have like 15-10 minutes in the end, so you can ask them. I will try to answer what I can and what I have the time for, but we will try to answer any questions during or after the webinar. So please ask if you have something. All right, let's go to the sources of error in positioning. So as I said, I will not go in the very basics of mobile mapping, but just to give a quick understanding of the technique we use here to get the data allocation, orientation, the accuracy. I have this slide here. So we have something called direct georeferencing. It means that the data will get a position and orientation on the fly. So we start from the field in the left. We have different kind of positioning or navigation sensors in our system. We have a GNSS antenna receiver, which will give us a global position. We have IMU, which is measuring angles and accelerations of the moving platform. Then many times we have something called DMI, which is a distance measurement indicator, which is giving us accurate distance we have covered, or velocity, of course, as well. Then we go in the office with this data when we do something called trajectory post-processing. And here we actually combine these raw observations of these navigation sensors through a thing called Kalman filter. It's a very sophisticated technique. Also in post-processing, we include GNSS base station, which will correct the accuracy of the GNSS and the GNSS position of the mobile mapping system. And from all this, we can generate something called SBET. In Trimble world, it's called SBET. It's short for Smoothed Best Estimate Trajectory. So this is the accurate trajectory path that the system went on the field. And this is the final result of our navigation data processing. And in the end, we have the final data. We generate laser data. We sync all different measurements, like the trajectory, to the laser data, to the imagery, and so on. And after this, we can go to different tasks like registration and colorization, whatever you want to do with the data. But the idea here is that today we talk about the two first steps of this workflow. So we talk about what we do on the field and what we do on the post-processing. And the next webinar will talk more about this registration, which comes after these two first steps. So this is kind of, I'm discussing the raw accuracy you get out of the system without any extra adjustment of the data. All right. So let's go to GNSS world. If we think about kinematic mapping, so we have a moving mapping, we call it a rover, so or in our case a mobile mapping system, and we have a mobile mapping system which is receiving this signal from the GNSS satellites, and we also have something called base station, which is receiving the same signals from the satellites. So this is pretty much the setup of GNSS world we have in mobile mapping. So let's go first to the most important thing about GNSS in mobile mapping. This is, of course, a number of satellites we have visible. So those of you who are familiar with the GNSS at all, you probably know that you will need 4 or more satellites visible to get a position solution. But more the better is the idea here. We have something called dilution of precision, DOP. And this is actually a value which describes the quality of geometry of the visible GNSS satellites. And this is something we can monitor. This is something what indicates us the accuracy of the solution you get from these satellites. And the best case would be when you have lots of satellites and they are evenly spread across the sky. And the DOP value is actually, the smaller it is, the better the solution should be. So for example, we have in our operating software, we can monitor the PDOP, which is position dilution of precision. And to give you some best practices regarding GNSS geometry and number of satellites, we have some tips we can give. So the first thing would be that you initialize the system. So start the mission and do the things you do in the start of the mission, and actually also collect the data when PDOP is low. And the value here is less than 3.0. So as I said, there's also a way to observe this PDOP value in the TMI. TMI is Trimble Mobile Imaging, the operation interface to the system. So this you can do on the field, observe it all the time. Also, if you're concerned about this, there's a lot of tools where you can actually pre-plan. You can see the sorry, technical issues, going back. So you can actually give your location and your time, and you can see how well the satellites are visible in this position this time. Of course, we have lots of different GNSS systems at the moment. We have GPS from USA, we have GLONASS from Russia, we have Baidu from China, and we also have Galileo in Europe now active. And one nice thing is that we recently got a new release of PostPack, the post-processing software 8.4, and this is the first time we are actually using Galileo as well in post-processing. And this might be really helpful in some cases when you don't have enough satellites, so you might have 2 extra coming from Galileo. It might be really helpful in some cases. But to get use of Galileo, your base station should also log Galileo signals in addition to the rover. Our mobile mapping systems are collecting data from Galileo as well. So if you're a PostPack user and you're under maintenance, you could upgrade to PostPack 8.4. Okay, the next thing which may give us some troubles is the GNSS outage. So GNSS outage means that we are in the field and for some reason the signals are not getting to the receiver. So they are blocked by natural objects. Many times this is a tunnel, this is a high-rise area in the city center, this tall trees next to the roads, stuff like this, which block the GNSS signal from the receiver in the mobile mapping system. And even a short gap might lead to a cycle slip, and this will give us slight problems. But during a GNSS outage, so when we are inside a tunnel or we are inside a city center, we will rely on IMU and DMI measurements. So we are not completely out of data when we are in the outage. I will explain a little bit more about IMU and how it behaves later. But to give you some best practices on how to handle when you are going into a GNSS outage. So the first thing would be that maybe you know that you're running into a tunnel. So make sure that you have the best possible navigation solution before entering this area. So you can do what you would normally do in the start of a mission, static logging of data and also dynamic logging of post data to get the best possible accuracy before entering this outage. And another thing is to get out of the outage as soon as possible. So more time we spend on the outage, the worse the solution will be. So it's possible to do this kind of, if you know you're driving a city center collecting data, you can do this kind of going in and out of the area, should be no problem. So you can get kind of fixed solution outside and then go into the outage and then come back and do this re-initialization after outage area. And one important thing regarding the outage areas is to use the MI. And this will actually help you quite a lot in tunnels and stuff like this. I will discuss about the MI also in one slide later. Another thing we face in the cities especially is something called GNSS multipath. In multipath effect, the GNSS signal reflects from any object, usually a tall wall next to the system. So as you see here in the left in the figure, we have this blue signal is the correct one, and the red one is reflected from the wall. It's very simplified drawing, but if this reflected signal is very strong, it might affect the measurements a little bit. We have good antennas to deal with this, but still there might be signals which get through. Some best practices, again, if you are driving in the city and you know there's a risk of multipath, you should at least avoid this kind of environment when you do the initialization of the system. So let's say you're driving in the city center. So you should do the start of the mission in parking lot or whatever where you have an open sky and no buildings near. Also in Prospect, there's something called elevation masking. This is something you can consider. 7.5 degrees by default, but you could get this up to 15% or something like this if you're thinking that some of the signals coming from a low angle could be a multipath signals. Also in Prospect, there's a setting called multipath where you can give it a low, medium, or high value. So if you know that there's a multipath, you might want to try this as well. All right, next thing, GNSS atmospheric delays. So our GNSS satellites are tens of thousands kilometers above us, and they travel quite a long distance from the satellite to our receiver. Actually, in simplified way, they travel to two different layers. And these layers are ionosphere and troposphere. Ionosphere is high up, closer to the satellite, and these both layers, they give us a small delay in the signal. We have to know this. And the ionospheric delay is related to sun activity, and the tropospheric delay, which is lower, nearer to the ground, is related to water and gas content of the atmosphere. And again, if you think satellite which is on low angle, the signal will travel a longer distance through these layers. So the effect will be higher from low angle satellites. We are quite good at dealing with this. We have scientific models which will reduce the most of the effect of these atmospheric delays, but still we are left with a little bit of a delay, what we have to take into consideration later. Some best practices, again, we can use the elevation masking if we know the satellites in the low angle might have too big delay to deal with. This is something you can consider. Another thing about the ionosphere is that sometimes when the sun is really active, it might affect also the GNSS signals. And to monitor this, we have something, for example, called I-95 index. If you put this to Google, you will find some information. So feel free to learn more about that through Google. Next, we go to base station. Mainly, base station has two things to consider, the accuracy and the correction interval. By accuracy, I mean when you set up a base station or when you use the base station data from another provider, it's good to know how accurate actually the base station is. So let's say there's a big difference when you set up a base station to just a known point in your area. Maybe you only notice accuracy of this point to a 2 centimeter level. And, that could easily add a 2 centimeter uncertainty to the accuracy of the whole data, like systematic error. So best practice always would be that you use continuously operating reference stations, so stations which know their accuracy to millimeter level. This is of course not always possible, but this is the best practice. Another thing you have to consider is the base station correction interval. So at what rate does the base station get corrections or give corrections to our roving receiver? And actually, I would not say this is best practice. This is more of a rule that we use 1 Hertz correction data. And the thing here is that our rover, the mobile mapping system, is collecting data 1 Hertz. That's why we need also 1 Hertz correction data. So if you imagine that you get correction only every 15 seconds, we have no idea what happens between these 15-second corrections. So that's why you need 1 Hertz. This is a rule, I would say. Okay, as now we have discussed about base stations and atmosphere. These are actually related, and this is why we use base stations. So the effect of atmosphere to the signal between base station and rover is something we have to consider. So the atmosphere effect is similar to us inside a certain radius, but longer the baseline is, the more this atmospheric effect will have effect in the accuracy. So if someone doesn't know, the baseline is the distance between the base station and the rover receiver. We have something called ppm factor, which is added to the expected accuracy. This means that the accuracy will grow in the distance by a certain value. The best practices here, always have a base station within 20 kilometer radius from your trajectory. This means that the Applanix, the manufacturer of this system, has calculated that inside 20 kilometer radius, the difference between the atmospheric conditions between the base station and the rover are not too big. So we can have a base station 20 kilometers far away. But of course, in many cases, it's we drive maybe 100 kilometers per mission, and then you would need more base stations along the trajectory. And this is pretty much that we have to use a correct kind of post-processing method in postback. And actually, we will have later on another webinar where we go into detail about postback processing. But those who are familiar with postback might know that there's different types of processing methods, and we should always use a correct one for all the types of missions you might have. Okay, that's it about GNSS. Next, we have IMU. IMU is again inertial measurement unit, and it's measuring us the accelerations and angles of the system. And depending on the IMU, we have, I would say, 3 different things we can talk about. We have something called repeatability. So that means if we turn on the system, it will have some offset from the true value. And if we turn it on again, will it have the same offset or more? And this is called repeatability. We have something called stability, which is the difference from true value inside one run, let's say it that way. Then we have also something called drift, which I'm going to talk more about in the next slide. This is something, as you would imagine, drift is something which grows over the time. So the accuracy or the error grows over the time. But to give some best practice again about how to handle IMU, the best way is to do a good initialization, meaning again the static initialization and dynamic initialization. So before we collect data, we want to give the IMU some dynamics, meaning we accelerate the car or we turn, we might do some sharp turns with the car to give the IMU some idea what's happening. Another thing is what we say is drive as fast as possible, but as slow as necessary. So IMUs actually like going fast, and this means more accelerations many times, and it will behave better when you go fast. And as I said, I will talk a little bit more about the IMU drift. This is a typical issue in some cases. So if you look at the figure in the left, there's the IMU moving in a coordinate system. The blue arrow is meaning that this is what we are actually doing. So we're going in a straight line, not too much dynamics. And the red line is something what the IMU might give you. So it's drifting to right in this case. And this is something what might happen during a long GNSS outage. So when the system doesn't have input from the GNSS for the location, the IMU might drift a little bit. And also this could be an issue in some scenarios where you are moving, even in good GNSS conditions, but you're not getting any dynamics for a long time. This could be, for example, railway data collection where you drive a long way straight and no accelerations and no turns. And some best practices how to deal with IMU drift. Well, in general, if you have a good IMU, you will have less drift. Also, if you're in a GNSS outage, you should try to give the system dynamics, so turns, accelerations. DMI will again help with the drift. It will give us some additional input for the Kalman filtering. And in some cases, depending on the system, also you could use GAMS. And GAMS is a secondary GNSS antenna which can calculate the heading accurately if necessary. But this is a special case, and also for GAMS usage, we will probably have another webinar later. But if you have questions about this, let us know. One slide about the DMI, why we use it. So actually, the DMI gives us some additional input in addition to GNSS and IMU for the Kalman filtering, so the combination of data. It gives us accurate distance we have covered. It gives us accurate velocity of the vehicle, but it also gives us something called zero velocity updates. So meaning that if we stop, it will actually tell the system we are not moving at all at the moment. And all of this might have a high effect on the XYZ accuracy during a GNSS outage. So we strongly recommend using DMI if you have missions where your GNSS is not perfect. So now you know what we can cover at this time about the positioning. Here's a table to show you some of the expected positioning accuracies from our systems. So you see here AP60, AP40, and AP15. AP60 and AP40 are inside MX9 system, and AP50 is inside MX7 system. Also, for everything, we have an open sky values, so where the GNSS is good, and we have a 60-second outage value, so meaning that we have spent 60 seconds outside of GNSS visibility, and we will have some kind of value to give you overview on how the system behaves during this. And these are again, of course, sigma 1 values, as we said in the beginning. These are post-processed using DMI, and actually the AP15, with the AP15 we also use GAMS. You get the heading value. And all these values you can also find from the data sheets of the system. So if you're more interested, please go into the data sheets of our systems. And in the end, about positioning, why we use post-processing. First of all, this is reliable. If you compare to, let's say, RTK, we don't have a radio transmission which could be interrupted. We are doing everything in the office later. We are more flexible in the way how we can choose processing methods, settings, and so on. And in the end, the post-processing is always also most accurate way of doing things. So it's the best in modeling the errors of your positioning. So we are always doing post-processing when we talk about mobile mapping. All right, that's it about the positioning. Next, I'm going to have a couple slides about the measurement errors. First, about the laser. Here I took the MX9 laser as an example. We have something called a range measurement error. So the error in the value of range we get from the laser scanner. In MX9, it is defined through both accuracy and precision. So we have 5 millimeters in accuracy and 3 millimeters in precision. So it's quite a small effect if you compare it to the positioning accuracy. And there's another phenomena which is called the laser beam divergence. So the laser beam is when it hits the object, it's not just a single very small point, it's a dot of a couple millimeters. And I hope you understand what I try to say here in this figure is that if you hit the tilted surface, the spot will be more like ellipsoid. But if you hit a perpendicular surface, it will be more like a circular spot. And this will have some effect also in your measurement. All right, next one slide about photogrammetry. This is especially what we use with the MX7, but of course also you can do this with MX9 and MX2. The photogrammetry method used is called space intersection. So we point same object from two images and calculate the intersection of these rays. If we look at the figures in the left, the first one in the left is I tried to model the scenario where the point we are measuring is a little bit far away and the measurement angle is not 90 degrees, which would be the best practice. This means that the P1.1 is the true value, let's say, and the P2 is what we get because of small angular error in the measurement. As you see, if you compare it to the right one, which has a, let's say, perfect distance to the object and perfect measurement angle, but with the same angular error, it will be a smaller error in the accuracy of the point we get. And things which you should consider when doing photogrammetry is the image interval, measurement distance to the object, measurement angle, which of course comes from the distance and the image interval. Also your picking accuracy, so how accurately you pick the point. This has effect. Also inside the system, the image stitching, the resolution of the image, and camera system calibration are things which affect this accuracy. All right, that's about measurements. I'm going to go shortly over calibrations, because of course calibrating the system is handling the systematic errors. What we can handle is called calibration. We have two types of calibrations. We have calibrations we can do on the factory when we manufacture the systems, and we have calibrations which are done by us in the support team or actually the users. So the first, the factory calibrations which are done before delivering the system are IMU, the GNSS lever arm, IMU, the sensor lever arms. These are both calibrated to millimeter accuracy. The laser internal calibration is done by the laser manufacturer. The camera internal calibration is also done either by the manufacturer of the camera or by us in the factory. And something very important is also the time synchronization between different sensors. But the more interesting one for our users is the calibrations which might change over time or which are done by the users. These are IMU, the laser bore side angles. So we don't know exactly from the factory how at which angle exactly the laser scanners are, and this is something we calibrate in support before delivering the system, but also if necessary during the usage of your mobile mapping system. So if you think there's a problem with the angles calibration, there's a mismatch between two scanners, this is something which can be calibrated by us in support. The same thing with the cameras. So for example, in MX9, we have two planar cameras where you can actually change the orientation. And if you do this, it should be, again, calibrated to match the another sensors. And this can be done by us in support, and in some cases, it can be also done by user. Then we have the two optional measurement units, DMI and GAMS. And this is something the user has to calibrate when he's installing the system to a certain vehicle. And of course, if we are on site training how to use the system. This is something we will train the user to do. All right, that's it about calibrations. Shortly, I'm gonna talk about error propagation model. So this model where we can combine everything we have talked about so far. So we can combine the positioning accuracy, we can combine measurement accuracy, and we can add also the standard deviations from calibration and calculate some values for the actual accuracy we get out of the system. I put here 2 examples. First, I took an effect of distance. This is something we can model. So this is a sigma 1 values for expected absolute accuracy of MX9 with AP60 in open sky. So at 10-meter distance, we would expect XY accuracy of roughly 3 centimeters and height accuracy of roughly 5 centimeters. And if our measuring point we are measuring is 50 meters away instead of 10 meters, we could expect XY accuracy of a little bit below 4 centimeters, and the height value is actually not changing too much. There's only one millimeter difference in the height. So the distance actually is not a major factor in the accuracy. Then another example I took from the model is comparing AP60 and AP40. So this is the 2 different types of positioning systems we have in the MX9. Again, these are sigma 1 values for expected accuracies. Here I have open sky values and outage values. So in the left, if you see AP60, we'll have very nice values in the open sky. But after outage, of course, the error will grow. And same thing for the AP40. And I draw these ellipsoids to kind of visualize the difference. So you would, if you can think of this as a 2D representation of the error ellipsoid. So in the vertical axis, we have the height error, and in the horizontal axis, we have the XY error. All right, that's it. I will now conclude the webinar. I hope everyone has learned something so far. So we could say that the accuracy is a combination of multiple factors. So you cannot just take one value and say it's always true. The GNSS will have the biggest influence in the overall accuracy, as you saw, but the measurements of laser scanning, of imagery, photogrammetry will have a minor influence if you compare to the GNSS. And one thing which is of course something to consider is the actual user accuracy. So when you do measurements from the point cloud or from the images, how well you are actually picking the points, or how well you are modeling from the point cloud. This is something you should also take into consideration. And more going into detail, if we think about positioning, we saw that it's quite prone to different error sources from the environment. First of all, the atmospheric conditions for the signal traveling from space to the ground, but also the actual physical environment, city where you're driving, or the tunnel, or the trees, and stuff like this. If you would put all the best practices we went over in a nutshell, I would say the first thing is careful pre-planning. So if it's possible, get to know your data collection area beforehand and do some planning, how you drive, where you do the initialization, and so on. And also be careful when you're actually collecting the data to monitor the PDOC, monitor the navigation solution, do necessary things when it's need to be done. And then later in the office, use correct post-processing method, use correct settings for your mission, and so on. And of course, now we only talk about the raw accuracy coming out of the system. And in the next webinar, we will actually talk about how you can maximize the accuracy. So if you have a too big offset, you think, to what you want to have, in the next webinar, we will tell how you can do some adjustment in the data through a registration. So the next webinar The title was again point cloud registration in TBC. It will be in 2 weeks on Tuesday. The times will be the same, so 10 a.m. and 5 p.m. of Central European summertime. So you can also already put this into your calendar. And even if you're in PTO, I think if you register, you will get later a recording of this session, so you won't miss it. So I strongly suggest that everyone who listens to this one and wants to understand the whole process here should also join this one. Now, we hope to see all of you here. All right, thank you. Now it's time for the questions, and if you have such a long question you are not able to present here, you can also send email to our imagings_support@trimble.com email, and we will take over from there. So I will check if we have any questions.
All right, Yoni. So I think we have a couple of questions here. I'll try to go through the list of questions and comment. So first question we say, can I use no Trimble base stations?
Yep, of course. So if it's a correct format for postback, for example, Rhinex, you could use Trimble base stations.
All right. Then we have a couple of requests from others who really would like to have the presentation. So I think this should not be a problem. So we could send the presentation to everyone.
Yep.
Yeah. So usually people get a link at the end of the webinar. Maybe tomorrow you get this link with the recording, and I think we can easily include a link to the presentation itself in the recording. So there should not be a problem.
Yep. Correct.
All right. So I think we have more questions. So there is, how is TBC set up today in terms of calibration working with mobile mapping data?
Oh.
Yeah, I think with this question you mean, is the user able to do the calibration by himself with the mobile mapping data with the current TBC state? Unfortunately, no, but this is in the plan. So at the moment, we say, okay, if you would like to change the orientation of any of the sensors on the laser, on the MX9, for example, then you would have to contact us, and we will do the calibration for you. But other than this, the plan is to indeed enable the user at the end to do the calibration by himself from TBC. Okay, I hope this answers this question. And then next we have, how long would be a normal drive when covering 1 kilometer? Well, I would say this depends on your speed. So how fast you can drive when you cover 1 kilometer depends on also the system and the point density you're using or you're willing to have at the end. So you could drive slowly, then you get much denser point cloud, but also with the MX9, covering lots of data and very high rate, I think you would you'd be okay driving fast. Another thing is saying, is 1 kilometer equal to 1 minute? I think this, this is really relative to how fast you drive. So you have to calculate this from speed and time. Another question, what accuracy in tunnels longer than 400 meters can be achieved, e.g., for example, in railways? It's a good question. Well, usually we would say in that sense, in 400 meters, if you were using the AP60 and you would cover these 400 meters in less than 1 minute, then according to the AP60, you lose nothing on the accuracy side. So with the AP60, you will not lose anything because it's 1 kilometer or 1 minute, whichever you reach first. And in that case, 400 meters, if you could manage to drive in less than 1 minute, then you would not lose any accuracy there, if we're talking about the AP60. Another big one, what does this accuracy value mean? 1 kilometer, 1 minute outage. Does this mean that you can expect this kind of accuracy by driving 1 kilometer and having 1 minute outage? No signal received, this would be the accuracy. Yeah, exactly. So it's whichever you achieve first, either 1 kilometer or 1 minute of outage. So whichever is close. So if you could manage to cover 1 kilometer faster than 1 minute, then these values apply, or if you cover the 1 minute before the 1 kilometer, then the values apply in that case. What is the influence of the driving speed to the accuracy? Yoni, want to comment on this?
Yeah, so basically the speed does not affect the accuracy too much. As we said, it's better to drive faster for the IMU, but it's more and more the speed is more of a question of the density of the data, not that much about the accuracy.
All right. What is the relation between the point cloud density and how fast you drive with MX9, MX7, and MX2? So MX7, we don't have point cloud, so we don't have any laser scanners. But with MX2 and MX9, yes, of course, the faster you drive, the further the scan lines will be away from each other. So this is the basically, but it will not affect how many points you collect per second, for example, because this is fixed. But the scan lines, which we call them the profiles, will be further the faster you drive. We have here another question. What's the recommended minimum speed for MX9 with AP60 and DMI? Gioni?
Yeah, I think we don't really have a recommendation for this, yeah. But as said, drive as fast as possible, but slow as necessary to get as dense data as you want. So no minimum, but I don't know if there's a scenario where you would need to drive slowly for any other reason than getting very dense data. But yeah, I hope this answers the question.
All right. Another one, it says better to have physical coarse base station with large radius, for example, 10 kilometers instead, or virtual base station with shorter distance. Well, I think it doesn't make much difference here if you have coarse or virtual base station, but I would say the closer the better, of course, because the ppm. So I would go for the virtual base station at 2 kilometers because why not? Yeah, maybe this would save me 1 millimeter or 2 millimeters. It's not so bad, but also having a coarse base station at 10 kilometers is still, this is great. So I think even the difference you would not even notice.
Yeah, and I guess the question is also what kind of virtual base station, how is the technique behind the VRS? So there are some differences between different networks. But I would say if you have coarse inside 20 kilometers, I would use it myself.
All right. What else we have here? We have a comment here about a relative accuracy, about relative accuracy of lasers, for example, let's say. So maybe Diony would like to comment about this, the relative accuracy between lasers, right and left. I guess this is, you covered this already in the calibration, for example. And basically relative accuracy is affected much by the calibration, but not only that, but there is of course a time difference between when a laser hits a target and the other laser hits the same target, because both lasers are oriented with a 90-degree difference. So it takes time for one laser to hit the same target that the previous one hit before. And of course, in this time period, there could be, or there will be a change in your GNSS error, for example, but we do not put much emphasis on this because we assume that it will hit it maybe after 2 seconds, 1 second, which is not long time enough for the error to fluctuate very high in between these two time spots, let's say. I think what is the relation here? We discussed this question. I think it's this is all. We covered all the questions so far.
think there are a couple new ones in the bottom.
I think it's all about what we discussed. We have lots of requests for the presentation, and yes, we will gladly provide this for sure. Oh, okay, it's more of a request. Do we have examples of data processed using MX9 on a boat? Say, for example, in a harbor or river Rhine. Oh, Yoni, do you have anything like that? I don't honestly.
I'm not aware of this.
Yeah.
So
we always say that the MX9s or the mobile mapping systems we produced are mainly for land usage, so not for marine. But it doesn't mean that it could not work for marine. It's just that maybe we don't have how it will behave in marine, because basically what we use inside our systems is a navigation system which is called LV from Applanix. And we don't use the MV, which stands for marine vehicles. So we use the LV for land vehicles. The problem with marine applications that in the marine applications, there is a motion called the heave motion coming from the waves. And the IMUs used in land vehicles are not dealing well with the heave motion. So they are not adjusted well to take care of the heave motion and compensate for that. So I don't think we have, of course, with the MX7, like I think in Amsterdam, we have a very good example of that they covered, I think, the whole city with the MX7, and that was really good. And even they drove inside the channels, but it's not something that that we would say we really have examples for at the moment, especially with the MX9.
Yeah.
Another question came, does measuring at night without imagery improve GNSS input by reducing ionospheric effects? It's a smart question, but yeah, I mean, I would say it would maybe improve the real-time navigation solution, could be, but not the post-process, because at the end of the day, we post-process our data with base station. Or what do you say, Johnny? Yeah,
well, I'm more thinking the actual ionosphere. What I understand about it is there's actual ions in this layer of the atmosphere, and this is not like it's not. That mean that when the sun is shining, you will have this, and when it's not shining, you don't have this. So actually, for example, if you're from Northern Europe, very north, you can see northern lights. This is caused by sun as well, and ions in this layer, and this is happening at night. So I don't think there's a correlation that much between night and day in the accuracy. But this is a very good question, and I'm not 100% sure. One thing you could do to check this is to Google the I-95 ionosphere index, and if it's lower and in the night than in the day, then it's could do a better accuracy for you. But very, very good question.
Yeah. Yeah. You should even write this question down and investigate more.
Yep. Correct.
All right. So I think we're also good on time now. So it's our allocated 1 hour is over.
Yep.
I think we have also no more questions. All right.
So, yep.
So yeah, thank you very much, everyone. And let me take this chance to thank all the attendees who took the time to attend this webinar, and we're really happy that you're here and you enjoyed it, and we're very happy to see you participating, sending questions. Big thanks to Yoni for arranging this and putting all the effort in putting the presentation. We will be happy to present this again today evening around 5 p.m. Eastern European summertime. So if you'd like to join us again, we'll be also happy. Otherwise, wish you all a very pleasant day and hope to see you in the next webinar in 2 weeks.
All right, thanks from my side as well, and have a great rest of the day. All right.
Thank you. Bye.
Bye.